Hey everybody, Corey and Victoria here. We are the Professors Du Bois, and in this lecture we're going to talk about emission spectra and the Bohr model of the atom.
And welcome back. And so we want to talk about, we want to get to the structure of an atom. So that's kind of where we're going in the next several lectures here. And we've learned about light, we've learned about frequency and wavelength, and I want to call your attention to a very common demonstration that's done all over. We would be doing it live. If we were live in front of you, we'd probably be doing this demo for you. But if you give energy to certain salts, so we use ionic compounds that have a different metal in each of these salts, and we give them energy with a flame. This flame is of different colors. So we have zinc gives us a yellow color, and strontium is very red, copper gives us this green color. So there's something different about these metals and these atoms that give off this different light. And understanding this light helps us go backwards and understand what is different about the structure of that atom, such that we end up with these different wavelengths of light.
So the idea here is we give energy to an atom, and when we do the flame test, we're just using a Bunsen burner. These salts that we use usually for the demonstration all have the same anion. So the difference is the cation, the strontium versus the iron or whatever. So when we add energy, the electrons in that atom go to what we call an excited state, and this excited state is a higher energy. They've absorbed some of that energy from the flame, and this isn't a stable place to be for that electron. It won't stay there very long, and it'll go back to what is called the ground state, or the lowest energy level that electron can go to. Well, when it goes back to the ground state, it releases that energy, that extra energy. And sometimes this energy is in the visible spectrum, and we can see it with our eyes. It might be in the infrared or in the ultraviolet, and we wouldn't see it, but that energy is released. So that's why we're seeing the different colors for these different salts.
Right. So if we had our different salts kind of over here, and we were, this is the incoming light coming in that we see from that flame test, right? If it's just regular white light, it's going to spread out into all of these different colors, this whole spectrum of light. But when we shine the light that comes from one of these individual elements, then what we see here, this is an example for hydrogen, that we don't have a continuous spectrum. We have these bright lines, these individual bright lines. There's actually 4 of them here. It's kind of hard to see the third and the fourth. But we have 4 lines. When we excite hydrogen and let it drop back down, those electrons drop back down, we have 4 bands in the visible region. And we also have bands up here in the infrared, and we've got some down here in the UV. And each of these bands, the energy that corresponds with those, represents the location that the electron came from to the location that the electron dropped down to. And that emits light, and we can quantify that energy, and it tells us something about those electrons and where those electrons can exist.
One thing that we kind of took for granted there is this light was going through a prism that separates the light into its wavelengths. So regular sunlight, or what we would call white light, will have all of the different wavelengths of light, whereas in this case we're looking at the hydrogen line spectrum. So that light given off by the hydrogen, it might look like a particular color for us, but it really just exists visibly of 4 different wavelengths of light. So on this next slide, we've got 3 different elements. We've got the hydrogen on top, and you can see those 4 a little better in this one. And we've got mercury and neon, and it kind of doesn't come as a surprise that there are more lines for the mercury and neon, because they have many more electrons, and hydrogen's only has the 1 electron. So this is the light that's been through a prism, or we use a diffraction grating that'll separate it into individual wavelengths. So that hydrogen light is not representing the entire spectrum. It's just 4 different visible wavelengths of light.
And Niels Bohr took this information and for hydrogen and surmised that, hey, there's only discrete levels that these electrons can occupy, because each of these steps that he witnessed, like the bright line spectrum, maybe that's one of them. Maybe this is another, right? So these energy gaps that he was seeing in the bright line spectrum correspond to the location, literal location and distance from the nucleus for the hydrogen. And so this actually only works for hydrogen, but it tells us an awful lot about the structure of the atom and how things work. So when we give this energy, the electron that is down here will jump up to a higher energy level, and then it drops back down. So each of these bright lines corresponds to a transition between these energy levels. So he has this model of the atom that the electrons are existing in like orbits around the nucleus that are in discrete distances away.
So here's just a look at kind of like a cutaway of the Bohr model, and we have an electron in the ground state over on the left, and that n number is a principal energy level. So n equals 1 is the closest level to the nucleus. We could see the nucleus in the center of the previous slide. And so that electron is in that first energy level, we're calling it n equals 1. And when some energy comes along of enough magnitude to excite that electron to a different energy level, that can happen. This is not a stable state. They call it an excited state. It's a temporary state, but that electron, when it goes back to the ground state, will release energy of that same magnitude. And one of the things that's interesting is it doesn't necessarily go to n equals 2, like in this picture. It might have been enough energy to get to n equals 3. And as it goes back to the ground state, it might go to n equals 2 first, or it may drop directly to 1. And both of those would have different amount of energy emitted. And that may be in the visible spectrum.
Another thing to notice here, sometimes we think of these as rungs on a ladder. I like to think of it as a ladder. So again, this is the cutaway that he was talking about. We were just seeing those levels here. So, the entire circle would continue around here for the Bohr model. But if it's like a ladder, if you think of it as a ladder, we can't stand where there's no rung. And the electron cannot exist where there isn't one of these energy levels. And that's why it's so interesting, this discovery that there's quantization of this energy, and this electron can only exist on one of these rungs. And that's why every single time we see like an n equals 3 or n equals 2 down to n equals 1, it's always the same bright line. It's always that same magnitude of energy. Another thing I want to point out is that these ladder rungs are getting closer and closer together as you get further and further away from the nucleus. So the first step is the biggest step. N equals 1 to n equals 2 is the largest energy difference, and then it gets smaller and smaller and smaller.
Now eventually there's a point where that electron just gets ejected from the atom. And sometimes that's written in on these lines, these Bohr models, and they use the symbol infinity, and that's called the ionization energy. And that's the amount of energy to create the ion, or to ionize the atom.
Right. So just like when we were talking about the photoelectric effect, there was a certain amount of energy that was required to eject the electron. Well, when you remove an electron or eject an electron, you've made an ion. So that's why it's called the ionization energy. And you might see this with the different lines coming up, and then all of a sudden you end up with an infinity, and it's just gone.
So Bohr was able to calculate the amount of energy for each of these principal energy levels. And he used this formula. The energy at some level n is equal to a series of constants. There's the Rydberg constant, which is new, Planck's constant, and the speed of light, divided by that principal quantum number squared, and that's just the energy level. And using this, he could calculate the energies at all these different levels, and then even calculate differences in energy between levels.
And this is just for hydrogen. So here's the formula. It's the same concept, just that we're subtracting one from the other because we're having a transition. So if we wanted to figure out how much energy is ejected when we go from the 5 to the 2, so this is n equals 2 down here. I don't know if you can see that, but so if we go 3, 4, 5, if we want to see what this energy, the amount of energy that was given off, and then translate it into a wavelength, we could do that with this equation here. Let's show an example.
Yeah, with the equation, we can get the energy. Then we have to use another equation to get the wavelength. We've already done that one.
Right. You might not see RHC. You might see this just represented with this amount here. So this is like a new constant. R times H times C, because they're all constants. All right.
So in this example, we're saying that the light, we want to calculate the energy of the light emitted. That says 1 mole. I think we were just going to, 1 photon. Good.
We'll do 1 photon first.
From 5 to 2. So this is a little bit confusing. We have to know, what's the initial and what's the final. So from 5 to 2, the final is 2. So 1 over 2 squared minus the initial, which is 1 over 5 squared. And what I do is I do my squareds first, and then so 2 squared is 4, and then I'll go 1 divided by 4 and just make that a number. And then I'll do my subtraction first and then multiply by that constant. The result here is 4.576 times 10 to the negative 19th. We get a negative value. And again, just like in thermodynamics, that sign is just telling us the direction of the energy. So that's the energy emitted or given off.
For that transition. Right. So we can use Planck's constant and the speed of light again and get back to a wavelength in meters. And then, of course, we can translate that into nanometers. And that was done for each of these drops down to n equals 2. And the drops that are down to n equals 2 happen to correspond to the 4 bright lines that we can see for hydrogen in the visible region. So here's an example of a question that you might see. So given these 5 levels, photons of the highest frequency, whenever I see something that wants highest frequency or longest wavelength or whatever, I always translate that into energy. So highest frequency means highest energy or greatest energy. So I want the biggest jump emitted, so these will be arrows that go down. So you might see a few different options here for emission. Maybe you'll even have an absorption in there just to kind of throw you off. So given these 5 levels, what would have the highest energy drop for emission? And that would be the 5 down to the 1. Be careful. You have to keep in mind that each successive step is a lower amount of energy. So here's your practice. Pause the video and give these a try. And here's your answers. Hopefully that was helpful to you.
Here we had to use the wavelength. They talked about the longest wavelength, so you needed to realize that the long wavelengths have less energy than short wavelengths. So there is a little bit of just understanding what is meant by wavelength and frequency for these types of questions.
Yeah, translate that to energy first, and then look at the question and get the largest or the smallest energy jump, or absorption if it's going up, emission if it's going down. Thanks so much for tuning in. We'll see you next time. Bye-bye.